The Earth is a global factory. At any given moment, somewhere in the world, someone is at work. Designing, producing, distributing the products and services essential to our daily lives. But what marvels of manufacturing lie behind these everyday objects? Internet cable, the tower crane, pencils, water supply, toothpaste. 5 ordinary things, 5 extraordinary stories. Now revealed as we go behind the scenes, inside the machines, to find out how do they do it. The port of Calais, France. In a quiet corner of the docks, this ship is taking on board an intriguing cargo. What appears to be a garden hose threads its way onto the loading bay at the stern. Strange enough. But stranger still, the hose seems to go on and on and on. The hose is in fact a massive length of undersea cable. The ship is designed to carry 4,000 kilometers of it. It's part of a global operation to keep the planet connected. Communication is the lifeblood of the modern world. Undersea cable makes it happen. It carries 80% of all phone, fax and data transmissions. Without cable, the modern world would grind to a halt. Most of the world's undersea cable begins life here, in a plant run by the Anglo-French cable venture, Alcatel. Manufacturing the cable is a delicate and labour-intensive business. The men on this shop floor have the delicacy of touch and the eye for detail of surgeons. The operation begins with this, a tiny filament of glass. It's called optic fibre. The fibre is impossibly small, just the width of a human hair, and it's designed to carry pulses of light from a laser. But even optic fibre has limits to the amount of signal it can carry. So, Alcatel weave the fibre together into an enormous piece of glass rope. The fibre rope is fragile, yet the conditions it will face are extremely hostile. So that means wrapping it in a protective coating. And here it is. It looks like ribbon, but it's made of high-grade steel. The steel threads its way through a complex array of pulleys some 15 meters long. It's an endless switchback designed to keep the ribbon perfectly aligned. As the steel and fibre bundle comes together, something remarkable happens. Miniature rollers squeeze the steel around the fibre to create the tube. A tiny welder seals the join, and the undersea cable is born. After wrapping in a waterproof plastic covering, the cable will be ready for laying. Back on the ship, the cable is coming on board at a rate of 100 meters per minute. It's a challenging pace. The operation needs constant monitoring. The cable is stored here, below deck. 2 giant tanks, each 7 meters deep and 19 meters across, can hold up to 2,000 kilometers of cable apiece. Enough to run from London to Warsaw, Poland, or New York to Denver. Specialist crews carefully coil the cable into place. Their aim, to make maximum use of the available space. The men work in shifts, each taking a turn to act as ringmaster, while the rest prod and push the cable tight with wedges. The storage operation will take a staggering 3 weeks to complete. Up on deck, there's more excitement. The crew is loading aboard a series of torpedo-like objects. They're called repeaters, and they have a vital job to do. Even with an electrical charge running through it, the cable cannot maintain the laser light signal at constant strength over long distances. So, along every 50 kilometers of cable, a repeater is spliced in to provide a boost. The loading operation may appear relaxed, but it's not. The crewmaster controls events with all the authority and subtlety of an orchestra conductor. Her team watches her intently. Few words are spoken.
Like a telepathic transfer of information, they just basically sign language or a nod of the head and a wave of the hand here and there.
Each repeater weighs half a ton. Damage it, and the cost of repair would run to thousands. Loading the amplifiers and cable is painstaking enough, but deploying it under the sea is even more so.
How I describe my job to people at home, the analogy I use is if you're in a plane flying over the Alps at 6,000 meters above them, and we have this string, this cable out the back of the plane, and we have to fill the contours of the Alps as we progress across the sea, you know, say from UK to America.
To lay the cable with such awesome precision means using some very special technology. So it's small wonder the ship's bridge looks like the Starship Enterprise. It seems quiet enough now, but when this vessel pulls out to sea, things will get very busy. The ship is custom built to travel at a speed of just 1 kilometer an hour, resisting tide and winds to stay on course via dynamic positioning propellers mounted out of sight around the hull. Soon the ship will slip anchor and head off on another epic voyage, inching its way across the surface of the sea. It's strange to think that so much effort on such a grand scale is devoted to something the size of a human hair. But optic fibre allows the modern world to talk to itself. Global communication today hangs by a thread, literally. It may seem an odd choice of career. The job is often lonely, the hours are long, the space is cramped. But for these trainees, operating a tower crane is their passport to cool. Go to any city and you can see them dominating the skyline. Giant tower cranes. Some cranes reach 62 meters in height. That's taller than Italy's world-famous Leaning Tower of Pisa. And they can lift up to 10 tons. So, how do they erect these leviathans? How long does it take? And why don't they fall down? German crane giant Liebherr has been building monster cranes for nearly 60 years. The scale of their plant is huge. The product they make is no less awesome. Cranes start life as giant pieces of sheet steel, some 8 centimeters thick. These giant routers cut and punch out the core components. The tower gives the crane its height. It's made from 4 uprights, braced by diagonal girders. The jib gives the crane its reach. A single girder this long weighs a lot. It needs a huge ballast on the back to balance it out. Moving back and forth along the jib, a trolley allows the operator to deploy the crane's hook to a specific spot on the ground. All these components define the shape and style of a tower crane, but none of them would function without this, a massive cogwheel called the slewing ring. It's the slewing ring that allows the crane to swing through 360 degrees with pinpoint accuracy while maneuvering loads of up to 10 tons. Slewing rings are precision pieces of engineering, and that means they have to be very carefully made. Rings have 154 teeth, each one painstakingly chiseled to a precise template. More teeth mean more resistance to the weight of the loads the cranes will lift. The result? Greater control. As the slewing rings are carefully tooled, so they're even more carefully assembled. Each ring weighs up to 4.5 tons. That's twice as heavy as a town car. Yet the workers here move them around the factory floor as if they were light as feathers. No less than 670 rollers are sandwiched between the top and bottom halves of the ring. The final movement must be smooth. It's not only a matter of driver comfort. Smoothness brings control. Control brings precision. And that's what cranes are all about. While the slewing assemblies take shape, back in the main plant, the tower sections are getting a coat of paint. Actually, 2 coats of paint. It's a massive operation. Now, the moment of truth. How do they build a tower crane? Erecting such a massive structure is easier than you might think. Construction is often completed in just a few hours. The secret? Tower cranes build themselves. The process starts at ground level. Heavy concrete slabs form a plinth, 1.5 meters thick and weighing 130 tons. That's nearly as much as a blue whale. On top of the plinth, the crew erects the first section of the tower. Around that, they install a special device, a 6-meter-high platform called the top climber. What does it do? Wait and see. Next, the jib and cabin arrive in sections on the back of a giant trailer rig. Each is assembled on the ground. The whole array is lifted by a mobile crane to sit on the tower's first section, directly above the top climber. Using 4 massive rams, the climber slowly lifts the cabin and jib inch by inch, creating a space between it and the tower below. The crane operator hoists up another section of the tower and the crew slots it in, underneath the top climber. The rams extend again and push the jib assembly up, and another tower section swings into place. And so it goes, until they get to the top. The crane is up, but how does it stay up? High winds tear at the girders with unimaginable power. Rain rusts and corrodes the steel. The earth itself slips and settles under the crane's enormous weight, loosening bolts, twisting joints. Lastly comes gravity itself. The constant inertial stress of swinging heavy loads can shear even the toughest girder steel. Back at the plant, these men are all that stand between a tower crane and disaster. The welders. The scale of the job is so big that even expert welders need a little help from machines. Together, they do a crucial job. The way the crane's tower sections are constructed provides the secret of its strength. Sealed welds mean that wind and rain cannot penetrate any part of the structure. Low wind resistance, 0 rust. The diagonals intersect with the uprights at the center of each box tower section. This means the points of force are transmitted down through the structure, making it incredibly stable. Cranes built like this have dominated construction sites for 60 years. But the demands of building are such that even juggernauts like these are no longer enough. Repair and building work must now sometimes take place at short notice and in very confined spaces. So Liebherr has created a rapid response unit. Enter the shape of cranes to come. The MK100 is the latest thing on Liebherr's books. A highly maneuverable, mobile crane that can build itself in just 15 minutes. And the entire thing can be controlled by just one operator.
When I work on the job sites, see the people there happy, and it's really great to work with it.
The MK100 is possibly the tallest vehicle ever created. There is no doubt the MK100 is coming to a neighborhood near you. It may have paid a visit already. But you blinked. It's been with us nearly 500 years, an all-weather universal tool so versatile it's even used in space. The pencil. The pencil is the most popular writing instrument ever invented. Worldwide, 6 billion are made every year. Yet few of us know the answers to a couple of simple questions. How do they get the lead inside the pencil? And what is the lead made of? The story begins underground. It's 6 a.m. in southern Germany. These miners are about to go on a quest. They're hunting for a special kind of rock. We know it as lead, because that's what it looks like. But actually, it's a different substance altogether. And it's what makes the pencil write. It's called graphite, a kind of metallic charcoal made from deposits of prehistoric algae, buried over 400 million years ago. Graphite is tough to find, even tougher to bring to the surface. "200 meters below the German countryside, conditions are dark, cold and dirty. Spotting graphite among ordinary rock requires a special knack. The miners use their ears. A bell-like ring means rock they're not interested in. A clunk means graphite. At shift's end, the day's haul is brought to the surface. After crushing, the rock comes here to giant flotation chambers. A powerful soap solution soaks away impurities. The sludgy graphite floats to the surface, where it's scooped into storage tanks for drying. Once dried, this batch of graphite is destined for a factory owned by the world's biggest pencil manufacturer, the 200-year-old German family firm of Faber-Castell. In the basement of an old castle, in what looks like a gremlin's kitchen, master pencil makers like Lothar Bogadine mix up batch after batch of pencil lead mix. The recipe involves mixing graphite with china clay. Just add water and set the blender.
It's like being a chef. You've got to get the mix of ingredients just right.
From the blender to the oven, the lead-making process continues. Forced through an extruder, the graphite takes on a recognizable shape. But although these may look like pencil leads, they don't behave like it. Before they can do their job, these unfinished leads still require baking and cooling. Until then, the leads are as bendable as rubber bands. After the oven comes the deep fryer. Leads are submerged in a bath of molten wax and oil. The more wax in the mix, the harder the pencil. Faber-Castell has come up with no less than 16 degrees of hardness, each defining a different level of the pencil's blackness. The graphite ore has been turned into pencil lead. But how do they get the lead into the pencil? The process starts with these wooden slats, each 18 centimeters long and 7 centimeters wide. At a phenomenal speed, a router cuts a sequence of grooves into each slat, one slat every second. What follows is a kind of sandwich making. First, the grooves are striped with glue. The conveyor belt divides. The graphite leads are laid into the bottom row of grooved slats. The slats are then glued together, top and bottom, with the leads inside them to form a basic pencil template. The newly made sandwiches then stack themselves horizontally onto a giant cylinder-like rotisserie. This slowly revolves over 90 minutes inside a big oven to cook the glue. If the glue does its job, the slats will bond into one solid piece of wood with no visible join. Gluing the slats properly is the secret to how they get the lead into pencils. As a new slat stack enters the rotisserie, so a cooked stack is pushed onto a conveyor which feeds it into another router. This is the machine that actually cuts the pencil shapes from the slats. There's very little waste. Each pair of glued slats will yield as many as 10 pencils. The pencil is made, but it's hardly finished. To stand up to the rigors of daily life, it needs a protective coating. And that presents a problem. People don't just write with pencils, they also chew them. The scientists working in Faber-Castell's lab faced a real conundrum: how to find a chew-proof coating. Paint would flake, plastic would peel. Eventually, the scientists came up with the answer: a water-based varnish. Standard varnish is spirit-based. It's toxic, but the pencil varnish is completely safe. Varnishing the pencils involves building up over 5 coats into the final color. After branding, sanders shape the front into a distinctive point. Before our eyes, a pencil is born. Like a concert pianist, the fingers of a quality controller dance across the pencils like piano keys. Instead of B flat, she's hunting for 2B, 4B and HB. It's a different tune, but the scale is just as demanding. Since this program began, the world has produced nearly 500,000 pencils, enough to stretch 90 kilometers. In the hands of an artist, a storyteller, a scientist, a designer, the pencil has a limitless potential. Tommy Johnson's family has been in the drilling business for 3 generations. Today, Johnson is working a few kilometers outside the city of San Antonio, Texas. As a Texan, you might think he's an oil man, but in fact, he's drilling for a natural resource far more precious. Water. It's a nail-biting job.
A water well is not worth 15 cents until you get water to come out of it. And the water's in the very bottom.
The people of San Antonio depend on drillers like Johnson for their very survival. Because, in common with 20% of the world's population, San Antonio gets its water from a source deep underground. It's called an aquifer. Johnson's drill head is biting through the tough Texan soil in a bid to reach one of America's largest underground reservoirs, the Edwards Aquifer. The Edwards is a massive cave system that descends as far as 1,000 meters below ground. Tiny conduits give way to cathedral-like stalagmite-encrusted chambers. Edwards is bigger than the entire US state of Connecticut, and it contains countless billions of liters. Indeed, there's so much water that in some places you only have to stick a pipe in the ground to release a raging torrent. But don't let this image of plenty fool you. Getting the water up to the surface and making sure the aquifer doesn't run dry is a major operation involving a dedicated team of engineers, geologists and hydrologists. So, how do they do it? The story starts with rain. When it rains in southern Texas, it really rains. And because of the region's geography, much of this rain quickly finds its way deep underground. High above the city, on the Edwards Plateau, hydrologists Gary Schindel and George Venny are hunting for gateways to the aquifer. The Edwards Plateau is made of limestone, a rock that's porous to water. If you look carefully, you can see the ground is riddled with fissures and caves, all carved by the rain.
It's important to map the openings, these conduits, these caves in the aquifer, to understand how it works.
Mapping the exact route of the water once it enters the cave system is vital for keeping a check on volume and quality.
I think of myself in some ways as a plumber. If you go to your tap and you turn on the faucet and water doesn't come out or it comes out dirty, you're going to call your plumber and he's going to figure out how the pipes are connected to figure out where the problem is. And essentially, that's kind of what I do.
Venny and Schindel work for the Edwards Aquifer Authority. The EAA must control the supply of water like a bank controls its loans. It releases specific quantities of water as and when it's needed. Like every other city in the world, San Antonio gets through a staggering volume of water every day. Toothbrushing, 8 litres a time. Toilet flushing, 16 litres. A 10-minute shower, more than 200 litres. Agricultural and industrial processes up the ante even more. 60,000 litres to spray a farmer's field. Making a reel of newsprint, 100,000 litres. All this demand adds up to one thing, a massive drain on the aquifer. And that gives the Water Authority an unexpected headache. These springs reveal why. The aquifer feeds into the San Antonio River. Diverting the aquifer for city use could reduce the river's flow. It's a problem facing many areas of the world that depend on groundwater for survival. Areas downstream of the city would be threatened with drought. The consequences would be unthinkable. So, the Water Authority must work out ways of using the city's water supply to replenish the river. And that means recycling. Engineer Daniel Martinez has an urgent task: to carry out a health check on the city's biggest recycling plant. To do so means climbing down into a hot, cramped chamber under the sidewalk. People stroll by, unaware of the crucial work going on just beneath their feet. The recycling station has been placed underground to preserve the beauty of the area. Its job is to clean the city's used water and feed it back into the San Antonio River to ensure communities south of the city get an adequate supply. All clear. The water is as clean as if it came straight from the aquifer itself. The farmers to the south can rest easy.
Can you tell the difference? One of these jars has our Edwards Plateau drinking water in it out of the Edwards Aquifer, and the other one has our recycled water in it. If you can tell the difference, have a drink.
Sidewalk recycling works for so-called grey water, the waste from baths, showers, the car wash. But for toilet waste, a much bigger operation is called for. This is the Dos Rios Water Treatment Facility, just south of San Antonio. It's an impressive name for an impressive place. But one breath will tell you what goes on here. It's a sewage plant. They call it brown water. Purifying this stinking gunge is a tall order. So, how do they do it? First off, these giant grinding blades filter out sludge and garbage. It's perhaps the foulest part of the job. The rank-smelling brown water is next passed through a giant concrete tank. They call it the aeration chamber. Nozzles on the tank floor supersaturate the water with oxygen. Why? Because oxygen is needed to feed the bugs. That's right, bugs. As the water is pumped into these huge outdoor tanks, it meets floating mats of green slime, colonies of oxygen-loving bacteria that eat their way through the sewage to clean the water. Perhaps strangely, the bug farm is odour-free. Insects eating the bacteria would create a bad smell, but the plant is home to a flock of obliging birds.
And we have a thriving population of purple martins that love to live at this plant, and they're sort of a natural pest control where we don't have to use pesticides.
So, between the bugs and the birds,
it's just a really pleasant environment.
After further filtering and laboratory checks, the water is at last ready to join the San Antonio River. Hard to think that something now so clean entered the treatment plant just a few hours before as a fetid-smelling mountain of muck. What a difference a few bugs can make. Limestone, quartz, rock salt, sand. Toothpaste is chock full of scouring abrasives that literally scrub our teeth clean. Amazingly, making toothpaste eats up a massive tonnage of rock, salt and sand a year. But how do they blend all those gritty minerals into a smooth, minty-tasting paste? And more importantly, how do they get the stripes in? It's early morning at the GSK plant just outside London, England. In just a few short hours, what starts out as a truckload of rock, sand and salt will soon end up as a mountain of toothpaste. To cook, a chef needs culinary tools, and making toothpaste is no different. What is different is the scale. These mixers are capable of mixing tons of toothpaste at a very high speed.
And we can actually turn over 5 tons in about 5 minutes. Essentially, it's just a very, very large kitchen blender.
The mega blender must churn the abrasive powders and the dyes and flavourings that go with them into a smooth paste. That means adding a gel and homogenizing the entire mixture inside a giant chamber.
The heart of the beast itself is this here, which is the homogenizer. We normally just call it a dishu.
It's a cute name for an awesome piece of steel. Inside the chamber, these enormous paddles are called agitators. They spin at 2,500 RPM, enough to get an average town car up to 30 kilometers per hour. The process may sound straightforward, but it isn't. The mix of powders and gel must be exact. One mistake can result in a toothpaste chemist's worst nightmare: lumps.
It's going to be mixed properly before it actually goes into the main mix. So otherwise you just get a lot of small lumps, big lumps. You don't want lumpy toothpaste.
Once mixed, the toothpaste begins a journey through a freeway of piping. Finally, the paste arrives here in a pressurized chamber. The plant contains hundreds of them. The chambers keep the toothpaste under 3 bar of pressure, poised, ready for injecting into the tubes waiting beneath. This batch of toothpaste is almost ready, but it's still missing one crucial feature: stripes. Stripes help define not only a toothpaste brand, but also its function. Does it offer extra whitening? Is it for use on sensitive gums? Above all, stripes are fun. So, how do they get the stripes into the tube? And how do they keep them from staining the white part of the paste? The answers lie in this lab. The technicians here must make sure that both white and coloured pastes have the same consistency. Scientists call it viscosity.
Viscosity is a crucial test we perform in the lab to ensure that the stripes don't run into each other and you're able to pump it out from the tube onto your toothbrush.
There can be no room for error. The technicians must check each batch that comes in from the factory floor. Even the slightest variation in viscosity could spell disaster for 5 tons of paste. It's a crucial part of the operation. The countdown has begun. This batch of toothpaste has achieved the target thickness. But how do they get the stripes into the tube? The secret lies with this specially divided nozzle. It keeps the stripes separate from the whites. The toothpaste has completed a momentous journey from quarry blasting to bathroom. All that now remains is to check whether it tastes good. As day follows night follows day, the Earth's global production cycle continues. The world never sleeps. We live in perpetual motion, creating, manufacturing, distributing. Since this program began, nearly 68 kilometers of internet cable has been laid on the world's sea beds. Thousands of tower cranes worldwide have swung into operation. Almost 1 million pencils have been made. The world has consumed 16 million litres of drinking water and used 55,000 tubes of toothpaste. Even the most ordinary objects often have an extraordinary story to tell. We only have to watch and listen.